Thank you, Raya. Yeah, I was kind of, reminiscing all this and, not crying, but, Anyway, I have to apologize for a number of things. First, for, forcing Lush on all my students, yes, and a bunch of other people. So to tell you a few things about this, this was a deep learning framework, very similar to what we know now, like PyTorch and TensorFlow and things like this, except it was first implemented in 1987. And the first functional version that used automatic differentiation with blocks was built in 1991. And then we realized that if we wanted to use this as a way of preparing systems for production, we had to write a compiler for it, because then we would be able to define our networks in Lisp and then hit a button and again, spit out C code that we could use in production. And this is how our character recognition systems were produced back in the early 90s. And so people who are implementing deep learning frameworks today are kind of facing exactly the same problems that we were facing at the time. We actually had a fairly complex scheme for dynamic graphs, because when you do character recognition, you have basically data-dependent varying graphs. And so we actually dealt with dynamic graphs back then, something that TensorFlow still hasn't figured out. PyTorch fortunately does, but it's very hard to do this in production efficiently. I'm going to actually reminisce about some of the stuff that Raya just mentioned, just because I think sometimes all keynotes start by going back in the past and then talking about the future and then talking about a little about how the present can help with the future. So I think an interesting question, I gave a talk at the Computational and Cognitive Neuroscience conference a few months ago, and Josh Tenenbaum also gave a talk there. And he said this at this conference: all of these AI systems that we see, none of them is real AI. And what he means by this is that none of them are AI of the type that we observe in animals and humans. And it looks like animals and humans are considerably more efficient at learning than all of the machine learning algorithms we've figured out. So we're kind of missing essential pieces in the system. And the preview of what I'm going to argue towards the end of the talk is the idea of predictive learning or unsupervised learning. And I'm not the first one to make that case. People like Jeff Hinton and Rich Sutton and various others have made that case before. So all of the applications of machine learning that we see, pretty much all of them, the practical applications, with a few exceptions, all use supervised learning in some form. Right? There is a few applications of reinforcement learning as well for ad placement and stuff like that, but it's mostly supervised learning. And of course, it's supervised learning applied to deep learning, to deep networks, and what we've seen over the last few years is an enormous inflation of the number of layers in convolutional nets and various other architectures, in the sense that what Facebook uses in production today for image recognition is convolutional nets, either ResNet or DenseNet or various versions of this that have been simultaneously designed to have many layers because it works better, but also minimized so that they can run efficiently. So in terms of volume, there's 2.1 billion users on Facebook, and every day they upload on the order of 1 to 1.5 billion photos. And every single one of those photos goes through essentially 4 convolutional nets, one that just tags the objects in the images, one that does content filtering, can filters out objectionable content, another one that generates description for the visually impaired, and the last one that does face recognition to tag your friends. It's turned on only in certain countries, turned on in the US, but not in Europe, for example. So if you run those networks on all the photos and a fortiori on all the frames of all the videos that are being uploaded, you're spending quite a bit of computation. So there's quite a bit of effort in sort of trying to kind of prune this down and make it run efficiently. But sort of rolling back the clock to 2003, which is when I left industry for academia, a DARPA program manager called Larry Jackal kind of came to us and said, could we use machine learning for robotics? And this was really my first foray into robotics. I was kind of either deciding whether to play with ground robots or flying robots. In fact, I gave a talk in Zurich in the picture that Aude just showed of that auditorium, and actually flew a Model I plane in that auditorium because I was sort of talking about flying robots then. But I decided to work on ground robots. So this Lager project lasted only a few months during the summer and fall of 2003, and submitted to RSS, the first RSS, and was rejected. Later submitted to NIPS and was accepted. And it was basically just imitation learning. So this was, I remembered talking or hearing about Dean Pomerleau's Alvin much earlier. I'd visited CMU in 1986 when he was working on this, or 1988 when he was working on this. And told myself, like, he should use a convolutional net, obviously, right? This is just at the time I was starting to play with them, and it sounded to me like if you had an image, as small as his image it would be much more efficient to use a convnet. So I had this in the back of my mind for a long time that I wanted to eventually kind of use convnets for robotics, and that was the first project. This actually used 2 analog cameras, not calibrated or anything. You just feed the 2 cameras to 2 channels or 2 sets of 3 channels of a convnet, and then just train the system to emulate a human driver. I think the total amount of training data was something like 20 minutes. This thing kind of worked okay. At least it worked well enough to convince DARPA to start a big project, which was called Lager. And I know there is, oops, doesn't show up. That's interesting. Apologies, just bear with me for a second. Not sure why this slide is not showing up, but we'll see. All right, this time it shows up. So I know I've seen a few people in the room yesterday who actually were participating in this project in different teams. I think there were 6 teams that participated, and we decided to use kind of pretty aggressive machine learning at the time, convnets running on the puny processors that were in the belly of this robot built at CMU, and we used a convnet that was kind of multi-scale and sort of looked at bands near the horizon, so that what the system saw was kind of more or less independent of the terrain. And the system was trained using labels collected from stereo vision. So we would just run a robot all around, then collect labels for stereo vision, register them with a location, and then use that as training data in the lab to kind of train the convnet to label every pixel as to whether it's traversable or not. So this was semantic segmentation. This is similar to what people now call fully connected neural nets, convolutional nets, but it was basically used as a sliding window for semantic segmentation. And then we realized that if we wanted the system to work properly in new environments, it had to essentially adapt on the fly. So collect local labels from stereo vision, and then train the last layer or last couple layers of the network on the fly to kind of adapt to new environments. And it would adapt in just a few frames, essentially. Because only the last layer would be retrained, and it's just a few parameters, and in just a few frames you get a lot of patches, and so it would work really well. It could do things like perform semantic segmentation in sort of monocular fashion and a very long range, and so the main contributors to this project actually are in this room, Raya and Pierre Samanet, who's now at Google Brain. And you're going to see them in this video in just a few seconds. So you run the convnet, you label every pixel in the image, you put the result into a map centered on the robot, which has this kind of funny mapping, hyperbolic mapping of distance. So it corresponds to the perceptual uncertainty that you have on distance. And you can use this for planning if you have a goal in the map. Unfortunately, this thing was running at only 1 frame per second, so it was not enough to avoid annoying moving obstacles like PhD students jumping in front of it. So there was kind of a second system running at higher frame rate using. So this is Pierre and Raya a few years back, about 10 years ago, and annoying this poor robot, but eventually giving up. And And so a couple of years later, we started with another student, Clément Farabet, who now works at NVIDIA, a project of perhaps kind of applying this idea of semantic segmentation, but to every, using more categories, not just for traversability, but for other categories, like, say, the road, the cars, the pedestrians, the sky, the buildings, the trees, things like that. And at that time, around 2008 or 2009, data sets for this were rare, but there were a few that started popping up where basically every pixel was labeled. It was only a couple thousand images, so it was not very favorable for convolutional nets because convolutional nets, as you know, require a lot of data. But it was just there so that the classical methods were working so badly that this was one of the few cases where convnets really were shining before the 2012 ImageNet revolution. And Clément managed to implement this on an FPGA and run this at 20 frames per second on an FPGA back in 2010, roughly. So that was kind of an interesting experiment where he showed that because convolutional nets have this particular structure, you can implement them in hardware really efficiently, run them on kind of relatively cheap, or not cheap, but sort of compact hardware. His FPGA card was about this big. And I think it sort of gave ideas to a bunch of people that started working on self-driving cars a few years later after it was kind of obvious that convolutional nets were a good idea. So in fact, I gave a talk in 2013, invited talk at the CoRL conference where it's a bunch of theorists, learning theorists. And one learning theorist in the audience, Shai Shalev-Schwartz, was just about to start a sabbatical at Mobileye. And he got to Mobileye, and he told the people at Mobileye, look, we should really try convolutional nets. And the people at Mobileye say, meh, no. I mean, it doesn't look like a good idea. Our chips can't run it. And so he ran the experiment himself, and he got much better results than whatever method they were using before, something like share boost or something like that. And from one day to the next, Mobileye switched to using convolutional nets. But now they had a problem, which is that the code, their chip was not designed to run conv nets. It had a convolver because in image, when you do image processing, everything is a convolution. But it really wasn't designed to run convolutional nets. So they had to shoehorn their convnet on their chip. Since then, I think they redesigned chips that actually are more appropriate for this. Soon thereafter, NVIDIA got the idea that they could also get into that business and sort of started working on this and eventually hired two sets of people. One is Clément Farabet, the guy who worked on this semantic segmentation system, and another person, Urs Müller, who is the CEO of the company with whom we collaborated on the Lager and Dave projects. Basically sold his company to NVIDIA. So what we've seen over the last few years is a lot of innovation in architectures. From the outside, it looks like relatively minor innovation, but if you look at the details, there is kind of a lot of a flurry of sort of different ways of connecting modules together, and some turned out to be really efficient, like ResNet, and some techniques for things like semantic segmentation or instance segmentation turned out to work really well, like mask RCNN that came out of Berkeley. RCNN came out of Berkeley. And so a lot of people working on this at Berkeley and at Microsoft eventually ended up at Facebook. And this is some work of this past year at Facebook by Kai-Ming He, from who is the ResNet guy, Georgia Gurchari, Piotr Dolar, and Ross Gershik. And they came up with this conceptually very simple architecture called mask RCNN. So it's the RCNN architecture that is normally designed for object detection, but it's designed to produce a mask for every object, and it's a mask that is instance specific, so it doesn't do semantic segmentation, it does instance segmentation. And I won't bore you with the numbers, but it beats the record on all the data sets that on which it's been tried. So it gives results like this, where you have 6 people or 7 people in this picture, and they're all kind of outlined or kind of filled in if you want. Of course, once you have this, it's easy also to produce a bounding box, the dog, the baseball bats, the wine bottles and wine glasses, really important if you're French. The backpacks and the umbrellas, the elephants, and the sheep. You can count sheep. You can always count sheep with instance segmentation examples. I'm not sure why. There's always a sheep picture. It works amazingly well. And this is one of those things where, if you kind of go back 5 or 6 years and you would have asked computer vision researchers, how long is it going to take for us to be able to solve this problem at that level, they would have said, well, I have no idea. It might take 10 or 20 years. But it happened faster. The same network trained it has different heads that are trained for different things. So one head is trained for instance segmentation. Another one is for detecting key points on human bodies, so you can kind of reconstruct the pose of human bodies. This actually runs in real time on a smartphone at a few frames per second. It's kind of a scaled-down version of that network. Perhaps more interesting so there's a lot of innovation in using convolutional net these days. One in particular, which I don't want to show slides on, but I just want to mention, which might be relevant for people doing mapping and SLAM, which is you can apply convolutional nets to data that doesn't come to you in the form of an array, but comes to you in the form of a function on a graph. So an array, you can think of an array, like an image, as a function on a grid graph, right, a regular graph. And of course, we know how to compute convolutions over regular graphs. You just do dot products and you do a sliding window. But it turns out you can define the convolution operation on irregular graphs. So if you have a graph with nodes, values on the nodes, and the nodes are linked by weighted links that indicate some sort of distance or something like this, you can actually define a convolution on a regular graph. It's if I use buzzwords, it's they're not buzzwords, but they sound complicated. If you do a diagonal operator in the eigenspace of the graph Laplacian, so you compute the graph Laplacian, you compute the transformation of the function on the graph in the basis of the graph Laplacian, and then you do a pointwise multiplication in that. That's like a convolution in the original space. So you can define convolutions on irregular graphs. And it's kind of cool because sometimes you want to, represent things like maps or 3D objects as graphs and sort of non-Euclidean domains, and you can still run convnets on that. There's actually a review paper that was just published. I'm a co-author on, but I'm a very minor contributor to it. First author is Michael Bronstein. Here is another example of sort of unusual use of convolutional nets. This is some work that was done at Facebook in Paris led by Ben Graham, who's before that was a mathematician, and he came up with this idea of using sparse convnets. He called it submanifold sparse convnets, SSN. There's actually an open source library for it, and it's basically the idea that if you want to apply convolutional nets to 3D data, like voxel representations, which is useful if you do robotics and you have a range sensor of some kind, most of your volume is going to be empty, and only a few voxels are going to be filled. Maybe 1%, 5%, something like this. So it's kind of a waste to run 3D convolutions on empty space. So you come up with this idea of sort of following the areas where there is data and then constraining the convolution to only produce data in sort of restricted subdomain. And this works really well and really fast. And in fact, with this, he won the competition that ended just a couple of months ago, called the ShapeNet competition, which is semantic segmentation for 3D objects, which I imagine would be useful for things like grasping, for example. The code is available, connected with PyTorch, so you can use that. Another use, which is perhaps less relevant to this crowd of convnets, is for translation. So some of the deployed translation systems by Facebook for translating certain pairs of languages actually use what's called gated convnets. These are convnets where basically the pooling is kind of a funny kind of pooling where there are switches to decide how to route the signal, and so there's a lot of sort of inventivity in this domain, and a lot of stuff that comes out of Facebook is open source, and you can just use it. A lot of it is hooked up to PyTorch. Let me skip ahead. Well, actually, not that fast. So here is an interesting example. There's also some work at Facebook. Most of that work I'm not involved in. I'm not a co-author on any of those papers. I'm just talking about other people's work. This is the first author. He is Justin Johnson. This was presented at ICCV a couple of weeks ago. And the problem here is to train a machine to kind of answer complex questions about images. So imagine you see the picture in the last half, the bottom right, and the question is, is there a matte cube that has the same size as the red metal object? And so you have to kind of figure out how to kind of configure a network to answer that question. And the way the team did it was to basically take the question, like, are there more cubes than yellow things? Run this through an LSTM. You get a vector that represents the question. Then you run this through an LSTM that produces what is basically a program, but it's a representation of a compute graph. And each node in the compute graph does a different function. Like, one module would filter all the yellow things, another one would filter all the cubes, and then on top of it, you put modules that count how many things are activated, and then you put another one that compares the two numbers and tells you which one is largest. And so the step of turning the output of the LSTM into this kind of program is discrete, so it's not differentiable. You can't propagate gradient to it. So that's sort of partially supervised initially with a few samples, but then it's trained using black box optimization, a reinforced method, for example. And everything is trained. The green modules are not pre-specified. They are trained also as part of the whole system, and the system kind of learns which module to activate for any particular situation. So it's a cool example of a dynamic graph that is constructed specifically to answer a particular question. And there's a lot of really interesting work in this area that kind of merges computer vision and dialogue. And of course, this is something you want if you're going to build robots that are going to interact with people and you're going to ask them questions and tell them instructions of what to do and things like that. So let me now talk about more of the future. What are obstacles to AI? And starting by noticing that animals and humans learn a lot more efficiently than all the systems that we have. We don't require a huge amount of labeled data. We don't require a lot of trials when we learn a task by reinforcement learning or something like that. And so a lot of people in neuroscience have been asking themselves in theoretical neuroscience, is there some sort of underlying principle in how the brain learns? Is it just a collection of hacks and kludges, or is there some sort of underlying, maybe one learning algorithm of the cortex? And it's not entirely clear what the answer to this is, but a lot of us are working under the assumption, perhaps, that there is sort of either an underlying principle or perhaps a few, basic algorithms, whether you think that word is appropriate or not, that sort of, underlie human learning or animal learning. And basic questions like, does the brain minimize an objective function? If it does it evaluate a gradient? If it does evaluate a gradient, how does it do it? It probably doesn't use backprop in the way that we understand it. And how does it handle uncertainty in prediction, which I think is a big question, as I'll come to in a minute. And really, the reason I'm interested in this question of why, how do animals and humans learn is because there is this holy grail of AI called common sense. Machines don't have common sense. And we don't seem to be able to get machines to have enough background knowledge about the world to have common sense, which is why it's very frustrating to talk to a bot, because if you go outside of their scripted domain, basically they can't really help you. It's very frustrating to build image recognition systems, which seem to work perfectly on test set, and then you change the conditions a little bit and they completely fail. And so how is it that we're able to do this? And of course, the first question you might ask is, what is common sense? And in my opinion, this is a very personal opinion, common sense is basically a substitute for learning the dependencies in the world, which is also a substitute for unsupervised learning, or as I prefer to call it, predictive learning. So, for example, if I want to learn how to represent the world, if I'm born with not a blank slate, because our brain are connected in particular ways, and there are kind of seeds for learning certain things really quickly. But it's unlikely that we are kind of hardwired with the notion that the world is three-dimensional, for example. And that's one of the things that's very easy to learn. If your brain is wired to predict what your percept is going to look like when you move your head, okay? Then the best explanation for how the world changes when you move your head sideways is the notion of depth, right? As a consequence of predicting how the world changes when you move your head, your brain has to come up with the notion of depth. It has to represent the notion of depth. And it has all the kind of right hardware for this, right? All the fibers coming from the two eyes, coming to the same place in the visual cortex. So you have to have the right kind of wiring, but beyond that, you can sort of learn this just through prediction. There's a lot of basic concepts about the world you can learn by predicting and then observing what happens and then correcting your model after having observed what happens. And so perhaps the idea of common sense is just filling in the blanks, whatever the blank is. So it means predicting the future from the present and the past. It means infer past events from a current percept. Filling in the blind spot, your retinal blind spot. We're not conscious of it because our low-level visual system basically fills it in. So there's predicting any part of present, past, or future percept from whatever information we already have. That's kind of predictive learning, and it's really another formulation of unsupervised learning. Because if you can capture all the dependencies between all variables in the world, that's basically the definition of unsupervised learning. Predict everything from everything else, essentially. And unsupervised learning is really the dark matter of AI because it's not something that is well defined. It's not easily testable. We don't have well-accepted techniques to actually measure the performance of an unsupervised learning system, which kind of sucks. So it's difficult to do science with it, but it's clearly something that animals and humans can do that we can do with machines. And animals and humans can learn really amazing things like object permanence. We learned that when we were babies. This baby orangutan here at the bottom right is being shown a magic trick where the guy here puts an object in a cup and then closes the cup and then shakes it and hides it for a minute, takes the object out, but the baby orangutan doesn't see it, and then looks at the inside of the cup, and his world model is broken, so he rolls on the floor laughing. Three things can happen if your model of the world is broken. It's funny, it's scary, or it's interesting, right? It's interesting. You pay attention where something unexpected happens because it breaks your model. And in fact, that's exactly how we can test in babies how, at what point they learn certain concepts. So this is a slide from Emmanuel Dupoux, and been talking to him quite a bit. He's a developmental cognitive scientist in Paris. And he does things like the stuff on the top left here, where you take a little track and you push it off support, and of course there is something holding it behind it, but it looks like it's floating in the air. And if babies are younger than 6 months old, they look at this and they say, yeah, sure, that's the way the world works, fine, no problem. Above 8 months, they look like the little girl at the bottom right. Oh my God, what's going on? And so you can tell whether it breaks their expectation or not. And so with this kind of technique, Emmanuel and some of his colleagues have been able to establish at what point babies learn different concepts, very basic concepts, like the fact that there are animate and inanimate objects that occurs around 3 months or so, or the notion of object permanence, that's a little earlier, sort of natural categories of objects, that happens pretty early. But the notion of intuitive physics, like gravity and momentum and things like this, it's about 8 months. It takes a while before we learn all that stuff. So how do we get machines to kind of learn background knowledge about the world by observation, like babies? So babies that age actually don't act very much. They don't interact with the world very much. They basically they get much more information just in than any kind of poking or action. But that sort of begs the question of why is it so good to kind of try to learn to predict everything from everything? And the argument goes back to many decades. This is an argument that Jeff Hinton has had for a very long time, saying that if you have a big brain with many free parameters in it, say 10 to the 14 synapses, Humans live for only about 10 to the 9 seconds. So we have way more parameters than data, and this motivates the idea that we must do a lot of unsupervised learning, since the perceptual input is the only place where we can get 10 to the 5th dimensions per second of constraints of information, if you want, right? So you need to feed complex learning systems with lots of information. You have to ask them to predict a lot of information if you want them to learn anything. And it's not necessary that this information be connected with a task, necessarily. You just need intelligent agents to be able to represent the world, regardless of what the task is that they are supposed to do. So for example, babies learn very early to distinguish phonemes. In fact, they can distinguish more phonemes than adults in the same country. And it's when they learn to speak that they lose the ability to distinguish certain phonemes. So the French can't make the difference between the and the after they learn to speak, but before they learn to speak, they can. Americans can't make the difference between un, and un. A lot of people who speak Asian languages can't tell much of a difference between R and L, things like that. So, we all know there are 3 types of learning: reinforcement learning, supervised learning, unsupervised learning, and there is sort of mixture thereof. You can mix unsupervised learning with reinforcement learning and sort of train the model and do kind of model-based reinforcement learning. You can do inverse reinforcement learning, also that has some sort of supervision. But if you take kind of the pure forms of each of those things, I've been showing this thing. I think the first time I showed this slide was actually a talk at DeepMind about 2 years ago, where David Silver was in the front row. And so it was slightly obnoxious on my part, but and this is slightly offensive to people who work on reinforcement learning. But the shock value of this is the fact that we have to realize how much information we're asking the machine to predict and how much feedback we're giving it at every trial when in the different modes of learning, right? So in reinforcement learning, the definition of reinforcement learning is that you just tell the machine whether it did good or not, right? You give it a reward, or you give it some percept that it interprets as a reward, which is kind of the same thing, right? It's a single value, essentially. Supervised learning, you give it the answer, and then you expect it to learn that. So there is more information you give the machine at every trial. And so necessarily, to learn any particular task, it's going to take fewer samples if you use supervised learning than if you use reinforcement learning. Okay, just because of the amount of information you give it at each trial, essentially. The model-free reinforcement learning has horrible sample complexity, essentially. Unsupervised learning, on the other hand, because you're asking the machine to predict lots of stuff, and at every time step you're showing it lots of stuff, you're giving it a lot of feedback. It's unreliable feedback, but it's a lot of it. It can learn more. Maybe it's not task-directed, but it learns more. And so, in that sense, I think a cat has way more ability to learn really quickly than any algorithm that we've devised, and probably has more common sense than any computer system, AI system we've ever built. So you should notice, for those of you who are big fans of reinforcement learning, which I am as well, this is a Black Forest cake, and so the cherry is not optional. In fact, it's got cherry inside as well. But pure RL is kind of hopeless if you're interested in self-driving cars or manipulation or things like this, because with model-free RL, you kind of, to learn to drive, you basically have to run off a cliff 50,000 times before you figure out how to not run off a cliff. First, to figure out it's not a good idea to run off a cliff, and second, to actually figure out not to run off a cliff. And so that's not really practical in the real world. It's okay if you do simulations, because you can run simulation faster than real time. You can run it in parallel on many computers. It's okay if you play Go, because it's, first it's fully observable, the action space is discrete, and you can run 10,000 of games, per minute or second, or millions of games in a few days. And so there are no problem. But there's one thing that really sucks about the real world, is that you can't actually run it faster than real time. Maybe it's a good thing, actually. But it sucks for learning, the fact that we can't run the real world faster in real time. And then anything you do in the real world can kill you, like running off a cliff. So So how is it that we can learn to drive without running off a cliff many times? And it's because we probably have one of those predictive models. We know what's going to happen in advance. If we turn the wheel in a particular direction, that takes us off of the road, and there's a cliff behind it. We have pretty good models of intuitive physics that tell us this is a really bad idea. And so we can do rollouts. We can use our internal simulator to kind of figure out what's going to happen as a consequence of our actions, and perhaps correct for it. But RL works great for games because you can run this really really quickly. It works, particularly for deterministic games. We have a bunch of projects in RL for playing StarCraft, which is a really challenging thing, and a lot of people at DeepMind are also working on this. We've also been participating in slightly violent games like Doom. Actually, people from FAIR won the last 2 competitions in Doom, probably because the DeepMind people would not let themselves actually participate in this competition. I don't know if we would have won if they had participated. We'll see. So this whole idea that you had to have a model and you have to kind of predict ahead in your head, goes back to, of course, classical optimal control, where you always use a model to plan. But the fact that you should learn a model goes back to Rich Sutton's Dyna architecture. And he has kind of a funny way of defining reinforcement learning in this paper. He says, the main idea of Dyna is the old common sense idea that planning is trying things in your head using an internal model of the world. This suggests the existence of a more primitive process for trying things not in your head, but through direct interaction with the world. Reinforcement learning is the name we use for this more primitive, direct kind of trying. And Dyna is the extension of reinforcement learning to include a learned world model. So it's funny because our vocabulary has changed since then. We still call all of this, we call all of this reinforcement learning. It's just that the Dyna style thing, we call this model-based reinforcement learning. But it's not just reinforcement learning. The idea of having a predictive model does not just apply to reinforcement learning. It applies to all kinds of learning, every type, really. And this idea of having a model of the world so you can do rollouts and then plan a sequence of actions in advance really goes back to optimal control. I mean, this is the way all of motion planning in robotics is done, and this is one room that I don't need to explain this to, contrary to other audiences, where you have your plant simulator, whatever it is, something that gives you the state of the world at time t as a function of the state at time t-1 and an action. And it's differentiable. And so if it's differentiable, you can do a rollout, and through basically backprop through time, also known as the joint system approach, you can figure out an optimal sequence of commands that will kind of minimize some objective function. That's normal motion planning, or planning in general. And so we know how to solve that if we have a good model. We can design objective functions, hopefully, or perhaps we can run them. How do we build models of the world? That's the big question. That's my obsession. And that's really what unsupervised learning is used for. So in my opinion, when we manage to solve that problem of actually learning world models, we're probably going to possibly kind of get to the next level in AI systems. And so the next AI revolution will not be supervised. I stole the concept for this slide from Alyosha Air Force. It might be televised, but not supervised. So, obviously the architecture of an intelligent system that we all know from RL, I mean, this is sort of an intrinsic motivation type autonomous agent where the agent produces actions on the world responds with percepts that are interpreted by the agent, and what the agent is trying to do is bring itself to a state that minimizes some objective function that it has, hardwired objective function, that measures its degree of unhappiness, essentially. Right? So the red box at the bottom tells the machine how unhappy it is, and it's trying to kind of bring itself to a state that minimizes the output of that objective, essentially. We have such a thing in our brain. It's called the basal ganglia. That's the piece of the brain that tells us whether we're happy or not, or we're comfy or not. So what does the agent have to have inside of itself? It has to have this world model, this world simulator. And it's not it's not like a physics engine of the type that we normally deal with when we do robotics. It's a trained system. It's some neural net of some kind that tries to predict future states of the world, at a low level or a high level, short term or long term, as a function of the action, so that we can use this for planning. So it has to be hierarchical inside and everything. And of course, it has to have some sort of critic that tells it whether kind of does a prediction of the long-term expected value of the objective, so that it can sort of form sub-goals and stuff like that. So in a particular situation, and for a lot of people this is very familiar, the system kind of gets an idea of the state of the world, then performs a rollout using its world simulator and a proposal for a sequence of actions, and then kind of figures out a sequence of actions that optimizes its objective, and then takes the first action, and then simultaneously trains a controller or an actor to actually directly predict this action without having to do this whole optimization. This is the way perhaps that animals and humans can compile new skills. When you learn to drive or you learn to ride a bike, initially you pay a lot of attention. You kind of think about what's going to happen if you do this or that. And after a while, it becomes automatic. Basically, the knowledge of it has been compiled into kind of your actor, which is basically feed forward, and it becomes subconscious. Right? So that's the difference between the sort of conscious reasoning and thinking ahead, and the sort of unconscious, subconscious, automatic action taking. So how do we learn predictive models of the world? There was some attempt a few years ago by some colleagues at FAIR, by Adam Lehrer, Sam Gross, and Rob Fergus, to train a ConvNet to predict what's going to happen to, say, a tower of wooden cubes. So it was trained with simulated data from a game engine, and then tested on simulated data and real data. And it does a decent job at predicting where the cubes are going to fall. So what you see here is an initial state on the left, and then you have what actually occurs at the top row, and then the bottom row for every single one of those 6 examples is the location, the predicted location for where the cubes are gonna go. And in some cases where the position is a little ambiguous, the predictions are fuzzy, right? Because there's no way the system can make an exact prediction, so it predicts an average of all the possible futures that can happen. And this is one problem we have to solve. How do we get machines to do predictions in the presence of uncertainty? And of course, from a theoretical point of view, it's simple. You just write this as a distribution and you're done, right? But then what's the distribution over the set of all video frames? I mean, just representing this is an unsolved problem. So we've done a little bit of like small experiments that I did with a few students. It's an archive paper where you learn a billiard ball model, and then you use it for planning. So when there is similar work at DeepMind maybe a year later, where there's some planning of like a spaceship in between planets and stuff like that. So you can use kind of learned models for planning. That's actually a very classical thing in control, right? You do system identification, and then you do planning using your identified system. Except here, all of this is done with neural nets. Let me skip ahead. So I just want to mention one thing here. There is one thing about predicting the future is that you have to remember the past. And there is a whole branch of work in sort of deep learning that attempts to augment neural nets, or recurrent neural nets in particular, with a memory, kind of an explicit memory module, which needs to be differentiable. So you basically build in software a RAM circuit, except you make it soft. So you reduce the gain of all the amplifiers if you want. I'm hoping there is sufficiently many electrical engineers in the room who understand what I'm talking about. But basically, it's a RAM circuit, a softened RAM circuit. And you can see this as an associative memory. And then you can, and there's several models of this that have been proposed. So DeepMind has something called the neural Turing machine, or differentiable neural computer. At Facebook, there is a bunch of those models, the kind of stack augmented RNN, end-to-end memory network, cache RNN, etc. So those are all kind of attempts, and LSTM can be interpreted in those terms as well. It's an attempt at basically telling a neural net, by default, just remember your past state and only change it when you need to. Here it's different. You have an explicit memory, and the recurrent net can access the piece of the memory that's most relevant for the problem at hand. So that's the soft RAM circuit. So you can use those things to do question answering and to drive dialogue systems. So that seems to be far from robotics, but in fact, the basic underlying mechanisms that you need for useful dialogue systems are very similar to a robot that interacts with the world. So here's a thing where you tell the system a story. You tell it, a description of a sequence of events, and the system stores that in its memory. So it's basically a bunch of objects and properties, if you want. Every statement is encoded as a vector. And then you feed a question to the system, and you ask it to answer the question. And during supervised learning, you give it the answer. And through backprop, it learns to access the proper relevant fact in the memory from the story to be able to answer the question. And surprisingly enough, those things actually work. So on artificial data set, but also on real data sets. And you can use them to do, so you can, those things can do sort of simple inferences, like, you tell them a story like Brian is a lion, Julius is a lion, Julius is white, Bernard is green, what color is Brian? If you assume all the lions are white, Brian is white. And if you want to build a dialogue system, you might need one of those networks to be able to predict what's gonna happen next in the dialogue. Being able to predict what the person is going to say next basically solves the problem of what should you say. Because if the person asks the question, or if you're going to give an answer and the other person is going to say no, is going to disagree, or is going to agree, then that means you know what is correct and what is incorrect. You know what's going to make the person happy or not. So being able to predict what's going to happen next in a dialogue is really useful. And in fact, this is an experiment that was done by Jason Weston and his collaborators at FAIR in New York, where they train a dialogue system to answer questions on wiki movies, and it's held through a dialogue. And what you see here is one of those memory networks being trained to hold a dialogue or answer questions on Wikimovie. And if the system has a predictive model of what's going to happen next in the dialogue, it learns much faster than if it doesn't. So the blue curve is the learning curve as a function of time of performance, and the learning is much faster than if you use kind of more traditional non-model-based type learning. So predicting under uncertainty is really the general problem on supervised learning. You have two variables, and there's some dependency between them. And of course, you can try to predict one variable from the other, but there is no single answer. It's never the case that there is pure deterministic relationships in the world between variables. Generally, there is multiple possible answers. So here, if I give you the value of y2, it's likely that there is two possible values of y1 that are compatible with it. And so the problem of unsupervised learning could be formulated in sort of abstract form as trying to learn a contrast function that tells you whether you are on the manifold, let's say, of observed data or outside. So during learning, this contrast function kind of learns to give you low values on the data that's observed and higher values everywhere else. And it's easy enough to train a neural net to produce a low output with a single output to produce a small number for things you observe. You can do this with gradient descent. How do you get it to produce larger answers for things that are outside everything it sees? That's the difficulty of unsupervised learning, really, in a nutshell. So one interesting solution, there is 9 or 8 different methods to approach that problem that people have come up with, including things like variational inference and stuff like that. Monte Carlo methods and all kinds of stuff. Sparse coding, sparse autoencoders, basically constrained autoencoders. Any autoencoder where the code in the middle has some pressure to not contain too much information, either because it's low dimension, like PCA, or it's sparse, like in sparse autoencoders, or you add noise to it, like in variational autoencoders. There's various tricks like this. Basically, they all serve to push down on the information content of the code, and that will actually have the effect that the reconstruction error will be small only for a subset of data, most likely the data you will train the system to reconstruct, and the reconstruction error will be higher as a side effect everywhere else. Adversarial networks, or adversarial training, is kind of a new way of handling the problem. So we want to do prediction under uncertainty, and the real world is not perfectly predictable. So, for example, I do the experiment where I put a pen on the table and I let it go, and I ask the machine, what is the world going to look like half a second from now? And it's possible that the system will predict something like the pen is going to fall to the left and the back, right? So the little video on the left here. And what the predictor can do is make a prediction, but it can make multiple predictions depending on the value of a latent variable z that I might draw at random or I might compute in some way. Okay, but when I vary z, the output of the predictor changes. Okay. Now, for one particular experiment, z is going to be drawn at one particular location, and the system is going to make, say, the prediction that the pen falls to the back and to the left. And then we let time pass by. And what we observe is that the pen actually falls to the back and slightly to the right, which is another point on this kind of red ribbon of potential plausible futures, if you want. Okay? So there's a whole set of plausible futures. We, even as humans, cannot predict exactly which point on this ribbon is going to actually occur. And so what we'd like is we'd like to be able to train the machine to make a prediction, but we don't want to punish it if the prediction it makes is not the exact one, as long as it's on the ribbon of plausible futures. Okay? So it predicted that the pen was going to fall, and it did fall. It didn't predict the orientation, but there's no way it can predict this, so we don't want to punish it for making that mistake. So what we need is a cost function that tells us whether we are on the ribbon or not. And that's basically what I was talking about just earlier. What is unsupervised learning? It's learning a contrast function to distinguish between stuff that can happen and stuff that cannot happen. Right? And it's the stuff that baby learns also by observation. When they go like this and get really surprised, it's because something has happened that they didn't think was possible. It breaks their model. So we need one of those things that computes whether we are on the ribbon or not. And of course, we can't build this by hand, so we're going to train a second neural net to tell us whether we are on this ribbon. And that's the idea of adversarial training. You have two networks that you train simultaneously. I'm sure many of you know exactly what I'm talking about and don't need to listen to this. But for those of you who don't, you have the green network here, the generator. It gets a source of random vectors. It makes a prediction. And then the discriminator, the red box, is trained to produce low outputs when it observes something coming out of the real world and higher outputs when it observes things produced by the generator. And those are the green points. So think of this little landscape here. The blue dots is what happens in the real world. The green dot is what the generator produces. And initially, they are pretty much random or bad. So this is backwards from the usual formulation of adversarial training, because I'm thinking in terms of energy, not probabilities here. And it's slightly more general to think of this in terms of energy instead of probability. So as the discriminator trains itself, this contrast function takes a shape. And of course, the generator is going to train itself to produce green points that the discriminator can't tell are fake. It gets the gradient of the output of the discriminator with respect to its input, and so it can change its parameters to put the green points at the bottom. And those two things can train simultaneously. There's a lot of instability in this thing. It's kind of a game that needs to reach an equilibrium, and it's not very well understood theoretically. There's all kinds of tricks like WGANs and IWGANs and cyclogans and stuff like that. So it works really well. You can generate bedrooms and funny objects and soft dogs, but more interestingly, you can do video prediction. So this is some work from a couple of years ago by Michael Mathieu and Camille Coupry and myself. And this is a kind of multi-scale convolutional net that is trained from an initial segment of video, 4 frames, and then is trained to predict the next 2 frames. And what you see here are 6-frame snippets of video clips, where the first 4 frames are observed. The last 2 frames that are indicated by the red contour are predicted. If you train with just least square, you get the kind of prediction at the top, which is blurry. It's basically an average of all the possible things that can happen. It's the same problem we were observing with the towers. But if you train with adversarial training, it just picks a good prediction, and the 6 other clips are kind of a representation of that. a similar system, slightly bigger, can be trained to predict what an apartment in New York is going to look like when you turn the camera around. And so you see this bookcase at the bottom. And as the camera rotates, the system predicts that the bookcase has to continue, essentially. So it sort of invents what the bookcase looks like afterwards. So it's captured some structure of the world. It's very short-term prediction, though. And it goes bad really quickly. So here is a slightly smarter idea, which is instead of doing video prediction in pixel space, you do it in semantic segmentation space. This is a paper that was presented at ICCV a couple of weeks ago. So it might be useful if you are in the business of self-driving cars. The fact that, so this thing predicts, those videos are half a second, but it can predict further into the future. And it predicts that if a pedestrian starts crossing the street, it's probably going to keep crossing the street. If a car in front of you starts turning left, it's probably going to keep turning left. It's very useful for self-driving cars to be able to predict in advance what's going to happen. Here's the last thing I want to mention. This is some new work. It's called error encoding networks. And it's so new that it's not entirely yet on archive. It will pop up on archive tomorrow. And the idea there is, when there are experiments that show that when you're shown very simple agent interacting, you can infer the action, the intent of the agent. So there's those famous videos, Josh Tenenbaum shows them sometimes, where you have kind of a room with two little triangles, and one triangle is trying to get into the room and the other one is trying to stop it. They're triangles, they're not people, but you kind of understand the intent. You understand what actions they're taking. And so this is a model that essentially attempts to predict whatever is predictable about the future, but then leave up to a latent variable whatever is not predictable, whether it's because there's an intelligent agent taking an action that you can predict, or because the world is being unpredictable. And the idea is the following. You have essentially what amounts to, it's not an autoencoder because it predicts the future. So X is the observation. It goes through, let's say, a convolutional net or something like this, produces a representation of the state of the world, and then it goes through a predictor that predicts the next state of the world or something like that, maybe a few frames in the future. And of course, there's going to be an error in that prediction. So initially, you can add to the internal hidden state of the system, you can add a latent variable called Z. And initially, you set it to 0. You have a switch here at the top that you can switch to 0, or you can switch to this phi box here on the right. But initially, you set it to 0. And so the system predicts whatever is predictable without any latent variables. And so it predicts kind of the average of all the things that can happen, essentially, kind of a central point, right? So in the case of the pen on the table, it would predict kind of a transparent pen, superimposed, in all locations, something like that. And so then you can compute the residual error. You observe the future, and you get the actual target that occurred, y. You subtract y prime, and then you take that difference and feed it to a trainable function, phi. And that function is meant to predict a value for z that will allow the system to actually predict y exactly. Okay, so now the latent variable is whatever is necessary for the system to actually exactly predict the future. But it's limited in its information content because it can only use the error, the prediction error of the system. And the result is that when you train this on like little, simple little things like a video game where someone is playing, or where basically everything is predictable except the action of the player, or like a little spaceship that you drive around or something with thrust, right? What comes out in Z is basically just the thrust. So you can infer the action. Whatever is not predictable is the action. And that goes into the latent variable. So that allows to kind of disentangle whatever is predictable from whatever is not predictable. So here's an example. This is using the dataset that Sergey, Chelsea, and a bunch of others put together, learning to poke by poking. And these are little videos where you train one of those systems directly on pixels. And what you see here are an initial state where there is an object with a robot arm. And the robot arm can poke the object in sort of random directions. And what you see here are generated potential futures as this latent variable changes, as this action latent variable changes. Okay, so it predicts that the object is basically going to stay identical to itself, except it's going to move a little bit, right? Which is exactly what happens in reality. So that's a little hint as to why making future predictions, I think, is an essential component for AI, and why we haven't solved the problem, and sort of a few hints about methods that might work, like this error encoding network, or perhaps adversarial training, or perhaps some other method that one of you is going to come up with in the next few years. Thank you very much.
Great. Maybe we could have a couple of questions while the next speaker sets up. Please come to the microphone.
Yann, thank you for that. I actually really like this, the example with the pen. So one of the things that's essential here is that the physics is indeterminate, right? And so what you're learning is to predict. What I'm trying to understand is that for manipulation, what we really want to learn is that uncertainty is inherent, right? That we're not going to actually be able to predict that at all, ultimately. So then we need to come up with a strategy that will actually be able to compensate for that. So I'm curious if you can say something about that really quickly, and I know we have very limited time, but I'm also curious if you could respond to Rod Brooks's assertions yesterday that driving is much further than we think. I'm curious about your perspective on that too.
Yeah, Rod said a few things about me yesterday. He said one thing that's perfectly correct, which is that every talk I give like a talk every week or something, and I only change a small number of slides every time. But the stuff about error encoding network, this is the first time I talk about this, so you guys are the first people to hear about this. So the driving, I'm more optimistic than he is. I mean, I think it's harder than what people think, because you have those marketing demos of cars driving themselves, but you have to make them really reliable before you can deploy them. But I'm fairly optimistic that they will actually be deployed relatively soon. So I'm not as Rod speaks from experience, because he has commercially deployed a whole bunch of robots in his life, and so he knows how hard it is, and you have to take that into account when you say something like that. But I'm actually, given the amount of investment there is in this, and how well this is currently working, I'm fairly optimistic. Now, dealing with uncertainty, okay, there are three types of complexities in predictive models. The first one is that even if the world is completely deterministic and completely observed, it might be that the dependency of the future on the past is very complicated, right? It could be just a very, very complicated dynamics, even if it's completely deterministic and observed. Physics is there to tell us that's the case, right? You have the three-body problem, right? It's chaotic. It's not it's not solvable analytically. So even relatively simple things that are deterministic and fully observable are hard. Second, it could be partially observable, still deterministic, but only partially observable. So StarCraft is in that category essentially. Not deterministic because there's another player, but if you take the two players, the game itself is deterministic but not fully observable. And that's the case for most of the world, right? We can't, if we play head or tail, if I had the wave function of the universe within a cubic mile, I could probably predict if you're going to do head or tail with a powerful enough computer, because it contains the entire state of your brain and everything, right? So it could be deterministic, but not fully observable, but still very hard to predict. And then the last thing is that it could be intrinsically stochastic. And so what I think a mistake that a lot of us in the RL community have done, we've made two mistakes. One mistake that Jerry Tesoro at IBM has been complaining about in his latest talks, which is that the RL community in the 90s made the same mistake as the machine learning community. It threw the baby with the bathwater, because there were no proof of convergence of model-based RL. It said model-based RL is crap. Because there was no proof of convergence of neural nets, they said neural net is crap. Let's keep to, in the case of RL, model-free or table-based things, and in the case of machine learning, let's keep to convex optimization. And that was throwing the baby with the bathwater. So that's I think a strategic mistake. And I wanted to go to another mistake which I forgot. So maybe I should take the second question.
Okay, thank you for a very impressive talk. One of the issues is prediction, or the predict coding, or the predict learning. So in case of the humans or the animals, the mirror neuron system, that is, some kind of, some constraint. So my question is it easy to involve such a constraint to some predictive learning, how to predict the future of the human being movement or the animal movements?
So you're talking about
how to involve such a constraint, the mirror neural system.
Which constraint? I'm sorry.
I mean, some body structures or something. So if in case of the humans' predictions, to predict the movement, so we utilizing our body structure some constraint. So my question is how to involve such a constraint to your network.
I mean, the question is whether you have to hardwire this constraint or whether it can be learned. And the flow of information we're bombarded with through our senses is so high that I think we can probably learn all those models. Now, if we are a simple animal that has to survive from birth, perhaps a lot of those things are hardwired. But I think for humans, it's probably a better idea to kind of leave that up to learning and adaptation. So the question is how much prior knowledge is necessary for kind of appropriate models of the world to emerge.
Yes, that's
And I actually had a public debate with Gary Marcus, who is a psychology professor at NYU, on this, organized by the philosophy department at NYU. He is kind of from the Chomsky school of thought in psychology, and so he was saying we need a lot more structure. We need like explicit, architectures in the brain for things like reasoning and symbol manipulation, and maybe 3D transformation of the world, things like that. Perhaps even intuitive physics. I was kind of arguing for the fact that we need to figure out what's the minimal amount of a priori knowledge that is necessary for the emergence of intelligence. I don't know what the answer is, though. But we need structure. Yes.
Let's thank Yann again.